So, please remember to rotate.
Yeah, okay. Hello, my name is Fedor. Yeah, and first thing, my handwriting is so bad. If you don't understand my handwriting, just tell me. And English is not my first language, so if I say something weird, just like ask. Yeah. First, let's start with a simple example. Everyone knows what a dot product is, right? Like it is covered in physics. So basically, usually we define a dot product of two vectors, v and u, as this, right? And we usually consider only two vectors. Or we can rewrite this as in terms of coordinates of both two vectors. So this would be a dot product for R2, a vector space R2 on R2. And usually we also can define the dot product on Rn. That would look like just yeah, and also we can define the dot product on complex numbers as well. So basically the topic of today's reading group is inner product. Inner product is basically a generalization of dot product on any vector space. So basically, an inner product is a function that takes any vectors v and u and gives and denote it as the following. So first, the positivity, the inner product should be greater or equal than 0. Then the second one. So the only possible way to get a inner product to be equal to 0 is just when the vector is equal to 0.
So that's important that it's not the inner product of something with itself is 0, if and only if v is 0. Yeah.
And also the additivity on the first entry.
Is that BD? Like the second one?
This
Yeah.
V. That.
Oh.
Wait. VV, yeah. And also the other fancy word is homogeneity. I don't know how to pronounce that.
Homogeneity.
Homogeneity.
I agree, it's a fancy word. I don't remember what the word is.
Basically means that we can factor out a scalar value from the first entry.
So it's just linear in the first step.
Yeah. And that's one of the properties of inner product. And the last one is it's called conjugate symmetry. So we can
Conjugate symmetry, I think it's also called skew symmetry. I don't know, it's called 1 million things.
it's like when you write a complex conjugate, it's like this line over, and you swap the entries. Do you see it?
Oh yeah, but must this exist for when you define an inner product over like reals or the conjugate?
The conjugate of a real number.
So the conjugate, like, we have a complex plane.
Mm-hmm.
So those are i's, those are just x basically.
Yeah.
When we consider like real numbers, we don't consider i's.
Yeah.
Conjugate are also like reflected
Yeah.
vectors across the x-axis. So if we have a z here, conjugate will be here. For reals, if
Yeah,
you
yeah.
reflect the real number,
It's just a real.
it's just a real.
So for real numbers, that condition is just nothing.
Yeah, exactly.
Well, actually,
It's,
no, it is useful. It just means that you can swap them
Exactly.
and nothing changes. So when we say number, we mean real or complex numbers. Nothing else matters.
Okay.
No other kinds of numbers out there, as far as we're concerned for now.
So another like example of a inner product or like continuous function.
So, I think you'll probably do this later, but maybe this is a good thing to mention to have people think about. So, okay, we have linearity in the first entry. Do you agree?
Yep.
Good. Now, what do we have in the second entry? So suppose this is an inner product over the real numbers. So the fifth thing, what does it tell us?
Commutativity.
Yes, so that u with w is just w with u.
Mhm.
Okay, but what does that mean about the second entry? Not Kevin, somebody else. So if the first entry is linear, what does that imply about the second entry in the real case?
Sorry.
So we have linearity in the first entry, and then we have condition 5.
Mhm.
If I take linearity in the first entry, combine it with condition 5 for the real case, what do I get? Yes?
Linearity in the second entry?
Exactly, linearity in the second entry. Amazing. So for in the real case, this is linear and this is a bilinear form.
Only for real numbers, though, right?
For real numbers, yes. In fact, it's kind of obvious. Like, think about the dot product.
Yeah, yeah.
It's bilinear because I'm just multiplying two things. Of course, it's bilinear. Now, in the complex case,
You get
what's
the
different?
conjugate, so then it-
What's different? Which part gets modified? Yes.
It preserves addition, but doesn't preserve multiplication by a number.
Exactly. So you would have 3, you would have the same thing for the second entry as 3, regardless. But 4 will be modified how? Somebody else. Condition 4 for the second entry will look how? I mean, you're probably going to talk about this,
Yeah.
but might as well have them solve it. So actually, maybe write the conditions
Should-
down right
should-
now while I'm saying that.
Should we like prove them or it's not?
I mean, just write them down because they can see the proof in their imagination. They can imagine the proof. So how would condition 4 change for the second entry? Okay.
Like that?
Yes, like this. That's what the difference would be. How do you check this?
Lambda is a scalar.
Lambda is a scalar. Yes.
Yeah.
So how do you see this? Obviously, by combining 4 and 5.
You just apply that one and then flip it.
Yeah, so you take 5, you flip it, right?
Okay.
Then now the thing is in the first entry, you pull it out,
And then-
but it's conjugate of the whole thing. So it's also, once you pull out the lambda, it's conjugate of the lambda, okay? Yes,
Okay.
because it's conjugate of the whole thing.
Okay.
And then conjugate, if you, an important property of complex numbers you should know about is that conjugate of A times B is equal to conjugate of A times conjugate of B.
Okay.
Okay, this is, you can check it, okay. So yeah, you have that property, and then property 3 is the same for the second
Do we need to prove the linearity for the second entry?
entry. Hmm?
Do we need to prove the linearity for the second entry?
I mean,
If you like,
how would you prove it?
yeah. Do you have any ideas?
Yes. Yeah, so you just write the proof.
Okay.
Well, that's just a statement. I want you to
Yeah,
prove
and
it.
then
Yeah. So use property 5 to reverse it. And you have forgotten to move the laptop.
oh, and then you can swap them again, right?
Yeah.
Yeah, and then you swap them down. Well, first you say that, oh, the sum of the conjugates is the conjugate of the sum is the sum of the conjugates.
Yeah.
There we go. Then you flip them, and then you just got the result you wanted to.
Okay, that's good.
So
Yeah.
very easy stuff. So yeah, the easy properties, the easy things, you should just ask them and
Okay.
not tell them,
Alright.
because otherwise they don't learn.
So another definition like this already mentioned in product space. It's just vector space with the inner product defined on it.
Question?
Mm-hmm.
Is it okay to assume, like an inner product is just an operation defined in a vector space?
Yeah, it's just a function.
A
That
function.
takes any two vectors from a vector space
Mhm.
and gives you like a number.
So it's so write it down in like as a function. Like what is the domain? What is the no, not there. Write it. You have so much space on this board. So not quite. Usually people don't put UV. They put two dots because that's like where the input goes. Yeah, this is conventional. Into F, where F is R or C,
Okay.
and V is over R or C.
Yeah.
But yeah.
Sorry, what's the first entry in the function?
It's
Here?
dots.
Just dots.
Dots.
Yeah.
Okay.
So next we need to forget about it for a bit, because we'll get back to that later. So we'll define like next two interesting things that Ivan proposed like 2 days ago. So first, there is a thing called norm. We'll define it later, like through inner products. But like, let's do it without names.
It's like a little aside. I suggest it would be cool if for the little aside you used a different colored chalk.
Okay.
I think that just would be interesting.
So we have norm. Norm is basically it takes a vector and gives a number, and has 4 properties.
Okay, I agree with you.
Mhm.
But you know, a norm is not something that takes a vector, gives a number,
Is it
and gives properties.
Is a function that
No. It's not what it is. What is the norm?
for the inner like
What
in
is
the
a norm? What does it do?
gives a length.
It gives a length, and the
Okay.
properties should be obvious from the
Yeah,
notion
okay.
of length that we have intuitively. So you should say, so you should give the intuition first,
Yeah.
and then say, because we have this intuition, this object has to do this, and here's the definition.
In a like general sense, like on physics or like math, we usually used to do, it's just like a length, like an absolute value of a vector, basically.
Yes.
But like, and also generalized to all the vector spaces, basically. But now we are not defining it through vectors, like inner product. We're just giving the properties. The first one is that it is.
So, sorry, once again, write the norm as like a function of from somewhere to somewhere. Yeah. I mean, just add it as a property. You know, just don't write.
Okay.
Remove that, and that it's not Rn. It's just R.
Yeah, right. So the first one is just the norm of a vector is greater or equal to 0. Second one, if it's equal to 0, if only if the vector is just 0. And the second one, or the third one is we can factor out scalar.
Yeah, I forgot about that one.
And the last one, we'll prove it later. This is the.
Hold on, stop.
Mhm.
What's the last one? What's the last thing?
You
that
you
we're
know
missing?
about it, like.
Intuition of length, right?
Yes, intuition of length. Like we want to define something, it's going to tell me lengths of vectors. Do you agree? And what's important is these are vectors, right? So somehow this thing should be related to vector space properties. Do you agree? What are the two things that can happen in a vector space? There's two things that you can do. Multiply or add. We have a condition for multiplication. Do you agree? So what do we still need? We need a condition for addition. What's the condition on the norm for addition?
We have where and then
Huh?
Your norm v plus
Imagine like
w is equal to
basic
the
geometrical like
Not equal.
shape.
Not
Almost, but
So-
like for all of the triangles.
from all
Yeah.
triangles.
First okay. Hmm?
Never mind. No,
Okay.
it's-
Consider like an arbitrary triangle.
Yeah.
Yeah.
Look at how does this length and this length compare to the length of the third side?
Plus. Oh, no more. Like the
So-
individual ones. The sum of, oh, it's like triangle inequality for.
Yes.
There we go. Finally.
Oh.
So which are vectors?
You know, things you knew since you were a child.
I don't
Since
know,
you were
like,
born, you would look at triangles.
Specifically, this is from V to R. It cannot be from like V to C.
That's the other thing. The function
Yeah.
has to be from V to R because
Like that's an exists complex.
length. What is? How can length be complex? This is a length. Just read this as a length of a vector. Okay, that's right. Good. So this is we define what it means. So we defined. We gave a definition of what could be considered a norm on a vector space, right? It's some function with these properties. In principle, I could have a vector space and give it many different norms, right? In principle. And, okay, go ahead.
And yeah, another definition we need to discuss is a metric.
Well, it's we don't need to discuss anything. I think it's important for us to discuss.
Okay, you're right. Great.
So,
So it's also a function that, but like.
no, it's not a function. What is it? What does it tell me?
Like it's how okay. Intuitive, if like in general sense, we can say that it's how we measure a distance between the points,
Yes,
basically.
that's true.
But like mathematically, it's a function. That
This is a physics reading group.
okay.
Wait, what? It is?
This is
Yeah.
a math and physics reading group where we try and understand things intuitively because that's easier to think about.
So important that it's not. It can be like any set of points, basically. Gets points and gives us a number again.
Is that a D?
This?
Yes, it's a function that we call D.
Yeah.
Okay,
So-
what's the key distinction between when we're talking about a norm and when
Yeah,
we're
they're-
talking about a metric?
Pretty much close to this, but like with some exceptions.
No. There is a key conceptual difference. Norms are on what?
Vector spaces.
Metrics are on,
What's X?
Just like any set of numbers.
yes,
Set of
Field,
points.
right?
any set.
Yeah, any set.
Of
Two R.
Oh,
2R. Distances and lengths are real numbers.
Okay.
Because I don't know what it means to have any other kind of distance or length.
Yeah. Or is it?
So a metric has to take 2 points and go to R. But the point is that we can define distances between 2 points using on any set if we really want.
So, like, if we imagine like basic geometry, what's like a basic property between like 2 points, like of the distance? If we like measure from x to y,
Mhm.
would it be equal to the same as from y to x? Is it like
Yeah.
makes
Yeah.
sense?
Yeah.
That's the one of the basic ones.
Let's get into geometry.
What else?
I wonder.
What do you think might be here?
The
Yeah.
distance itself is zero.
Great.
Oh, come on,
Let's go.
Okay. The third one. Great.
Pretty good.
And the last one?
Sorry, so you had dxx equals 0, and then you want to specify this strictly greater than 0 if x is not equal to y. right? The point is you want to be able to use the metric to tell points apart, in the sense that to tell points apart.
And the last one, which is on the board already. But like with different words, like different symbols.
Obvious property of a
We- like
Okay, there's some things written on the board, and
Yeah.
so guess. You will
Guess.
eventually get it.
we were discussed that like
Yeah.
2 minutes ago,
Just guess.
So I already
You're
answered
on a
two,
roll, bro. Hard
like
as hell.
3 minutes ago, right?
3 minutes ago?
Just guess
Triangle
something.
equality?
Yeah.
Yes, that's right.
What? But wait.
Like the distance.
So wait.
From X to Z.
No, just like
Y.
like from R to R.
Less or equal than just from X to Z.
Concentrate.
There's less of this. Question. The last property is the only property that we can relate multiple different points.
Yes.
Yeah.
And it's the only one we need.
Yep.
Yes.
So,
Okay.
yeah. And the question is, how can we?
And just digression. In some languages, the track inequality is called donkey's inequality. Because if the donkey wants to travel from point A to point B, it takes the shortest path, which is this
Yeah.
way.
Yeah.
That's a good
basically.
point. I'll memorize
That I didn't know that. That's good.
So, also another
That's
thing
okay.
is that we can define a metric using a norm. Does anyone have any ideas how we can define a metric, like a function that takes basically 2 vectors? Mm-hmm.
Just make X like the R here. Like you take a
No,
norm,
we
you
need like a
produce
function. We need a function like
Yeah,
a,
so compose a norm and a metric.
No, norm is just any function, like with certain properties,
Uh-huh.
with these properties.
So you can
So you need to define like a norm.
And a
You need to
product.
use like a norm to define a metric.
Yeah. Take your inner product. Is your inner product no, it's not.
It is also like a. We already have done that, like on maybe geometry or physics classes.
So like from the 0 point.
Huh?
Okay.
So we have two vectors
Yeah.
basically.
Yeah.
They can represent like 2 points on a
Yeah.
So you
system.
subtract them.
That's it.
Yo, it's
So-
all physics, bro. It's all just physics.
You have two
It's not even physics. It's Pythagorean theorem, essentially.
Yeah.
It's all
Whatever.
just Pythagorean theorem.
I don't know.
That's it. This is like basically a metric defined through the norm.
And if you were to sit down and say assume the norm does that, you can show that that will do that.
Yeah. If you want, you can check that.
Yes.
Just as an exercise.
dVu is equal to oh wait.
That's it.
University takes the intuition out of you, man.
Yeah.
That's so obvious. What the heck?
So, okay, let's get back to inner product. Now we are again defining a norm through the inner product, which is basically really not like in high school. So,
You want to use maybe a third color now that you're talking about the third thing.
no, just a regular one.
Yes. The digression is.
What do we just call metrics?
That's it. Norm is just like a square root of the inner product with like a vector with itself. And basically, if you think about like, consider that R2,
Mm-hmm.
and you have like, let's say, this point and this point, right? And you have a, if you take a dot product of like two vectors, this one and this one. Oh no, wait. If you take this vector, right? Take a dot product of itself. That would be x squared plus y squared, right? And which is basically Pythagorean theorem. And then if you take a square, you'll get this like length of this triangle.
Just to be clear, we are using the same, is that U?
V.
Okay,
Yeah.
using the same V.
So this is like example from. So as we said, like basic properties of a norm is if a norm is equal to 0, basically means that the vector is 0, if and only if. And we also can factor out the following one here. So another definition is when the dot product is equal to 0. When? Like when is it 0?
Cosine theta.
Like
Orthogonal.
yeah. So another definition of
For subproperty 2 of norms, you take the absolute value of the scalar.
yeah. For complex numbers, the absolute value would be
It's just
for complex numbers.
as expected.
Just like
Reasonable.
I think that would be helpful.
So why are they called orthogonal intuitively?
They're perpendicular.
Perpendicular. Why are they perpendicular?
Wait, what?
So why does the dot product being 0 mean the vectors are perpendicular?
Where's our?
Oh, there's no projection, right?
Why? Simple picture. The first thing that was said. The first thing that was said that u dot v was equal to magnitude of u times magnitude of v times
Cosine of
times
theta.
cosine theta.
Oh,
Okay,
it's
if that is 0, that means that
Oh, cosine theta
that
is-
theta is 90
90.
degrees. Good.
You have to take the projection.
Yeah, I mean it's the same thing, but okay. You should be able to.
The answers to your questions are so like. Are we just overthinking this?
Yeah, that's the whole point. The whole point is that you're always overthinking it. It's not that deep.
So now it's time to prove it. But
And if you think it's deep, then it's you don't understand it well.
okay, can I erase that?
Yeah, sure.
Wait, how did this switch from V and W to W?
I think it's.
Oh.
A little typo.
No, it's just a weird W.
I think you should use your imagination to fill in the blank.
And it could be like a special property, you know?
So that's the other thing. Sometimes the typo is like meaning changing, and sometimes the typo is clear what the typo is.
You can tell it's a typo, it's not really a typo.
Spell that. Pythagoras.
Exactly. That's right.
Oh. Orthogonality is defined not by some other property other than the fact that it just equals 0.
What?
Orthogonality is not like in physics how you say, oh well, cosine of theta equals 90, and so that's orthogonal. It's just the thing equals 0, and that's orthogonal.
Yes, but so the idea is this generalizes the like our intuition in R2 and R3.
Mhm.
And so in R2 and R3, orthogonal literally means they're perpendicular.
Yeah.
So now we kind of use that as motivation to define this to be perpendicular to each other.
In higher dimensions, this concept of degrees doesn't exist, right?
Of degrees,
Yeah, like the angles between like vectors.
you could define. You could once again define the, just say uv equals cos theta,
Okay.
and use that to define angles between vectors.
And
If you wanted to.
Okay.
And you just kind of go the reverse way.
Okay.
The thing is that it's just those angles might not mean much.
Yeah.
Yes, question.
Oh, yeah, I was about to say.
Okay. Okay, I was like, this
Yeah.
cannot be right, so they'd have to be perpendicular.
So-
Sorry, parallel.
That's the easiest proof of Pythagorean theorem, I think. Basically, we can rewrite the norm squared as a just like a linear product of that, and then use the linear, like the one of the properties, to just factor everything out. Okay, and this is 0 because this is because they're like orthogonal by the assumption, and these are just the norms squared. That's it.
So this is great because we had a Pythagorean theorem for perpendicular vectors in like the usual sense, and now we have it again in our generalized sense.
So another thing that is important, we might want to rewrite like one vector u as a like scalar multiple of another vector plus another vector. Basically, if we have like one u, we want to know how to rewrite it in terms of v and like some other vector orthogonal to v. And basically, we would want to do a certain like algebraic operations here. So we want to find a certain constant c in that case, so that those two vectors are orthogonal or equal to 0.
Is one of those a V?
Yeah. This is v, this is v. Which is just v minus 0.
Does this say you can make any two like vectors orthogonal?
Hmm?
You can make any two vectors orthogonal.
You can rewrite one vector u in terms of like other vector and like another one which is orthogonal.
Oh, okay. This is like
Yeah.
drawing the triangle.
Yeah.
Yes.
Okay.
A little bit skewed. My apologies. So, and then now we know C basically. We can rewrite C as a
So I think this is worth stopping for a second for. So yeah, actually, can you rewrite this expression again? Rewrite this, but with C like substitute.
yeah. So yeah, I was
Just rewrite the same thing and
Mhm.
substitute, and then we can interpret the equation.
So, and in this case, W would be just this vector. So, And this, like, you can see that. So,
Yes, so let's think about this just for a second. So we see that kind of U inner product V, right? It looks like, you know, it almost gives me the projection of like the component of U that's along the direction of V. Do you agree? But then I have to divide by the norm of V, because really what I want to do is take U dot like V hat, so like V, a vector that's unit length 1 in the direction of V, so I have to divide by V squared, okay? And so, okay, I get that from there. And then the second part is quite literally, I take the vector and then subtract off the bit that's parallel to V, and I should be left with the bit that's perpendicular to V.
another important concept is orthonormal.
Okay, wait, hold on. Did people understand that problem?
Are we talking about like U equals?
So, yes.
Okay.
Just look at like the
Yeah.
line above it.
Yeah, yeah.
U is equal to that plus U minus the same thing, right? What does that mean in terms of this picture? This means I take U, I use the inner product to
Mhm.
find kind of the bit of U that's along V.
Yeah.
Do you agree?
Mhm.
Okay. And then I multiply that by V. That just tells me the component of the component of U that's like parallel along V. I got it. Don't worry. The first thing is the component of U that's parallel along V.
Yeah.
And then the second thing is like, okay, let's just take U
Mhm.
and subtract off the bit that's parallel along V. That will just give me the bit that's perpendicular to V.
Yeah.
And so then
That's
that
W.
second part should be W in that diagram. Yes.
Okay.
And this idea we will use countless times.
Yeah, it's just this fancy
This is also like
re-expression
that's a
of the-
generalized way of like the dot product we use in physics to get.
Yeah, like everywhere where you see like the little brackets,
Mhm.
you should be able to rewrite dot product, and
It works
it's all the same.
Okay.
So,
Go ahead.
next, when we talk like about the coordinate system, usually we consider again unit vectors that are orthogonal to each other, right? And usually those unit vectors have a length or like a norm that is equal to 1, right? So that's why we introduced another definition, which is called orthonormal. This is basically those are orthogonal vectors that have norm equal to 0. That's it, and they're denoted as like through E.
Orthogonal vectors with norm equals
Yeah.
Wait, the
Norm
norm was
equals-
1.
Oh,
0. Yeah, I was
my
like,
bad.
I was like, hold on.
Yeah, my bad.
Yes. Yes.
Just through E, yeah. And then there are also.
So, sorry, you're being a little bit not careful. What is orthonormal is if you have a collection of vectors.
Yeah.
The collection of vectors is orthonormal, meaning any two are orthogonal to each other, and the norm of each is 1. So that is what is meant by this.
These are just your XY Z axes.
Not sure, but not necessarily.
Okay.
Right? Like that is if I took E1 E1, E2, E3,
Yeah.
that is an example of an orthonormal set. But I could always, you know, kind of rotate it into whatever and get a different orthonormal set.
And there are also pretty good properties.
Well, so the first one is
This is just a application of Pythagorean theorem, and the fact that the norm of any orthonormal vectors is 1. So when you apply Pythagorean theorem, you'll get like.
So this is for an orthonormal set of vectors.
Yeah.
Yeah.
if you rewrite this as like a Pythagorean theorem, you'll get yeah.
And since the norm of E is just 1, you'll get this. And yeah, the next one is
I have a question.
uh-huh.
All these like little details, if I place it in a 3D map, and like say like, I don't know, with Desmos 3D, it should make sense. Like if I square E.
If you square E,
Yeah, E is just like it's like the unit vector thing. And so if you square
squaring E, it doesn't make sense to square a vector.
well, the length of it, right?
Okay, squaring the
Yeah,
length of it
that's
makes
what I'm
sense.
saying. It should intuitively make sense.
You square
Everything
one,
on.
bro.
I mean, it does intuitively
One
make sense.
squared is
What
one.
doesn't intuitively make sense?
No, I'm just asking you. Everything we're talking about, if it doesn't intuitively make sense, I'm thinking of it wrong.
I don't know. Maybe you just have bad intuition.
Wow.
I don't know. You know, the goal is that by the end
Mhm.
everything is intuitive.
Okay.
Maybe at the beginning it's not.
Alright.
Okay, similarly, when we again consider the 2D plane, we have a unit vectors, right?
Yeah.
And basically, from the algebra perspective, those unit vectors for like x and y axis, they are like just a basis
Mhm.
of that.
Yeah.
Usually, we want to like have a basis that is like nice and neat, right? So that's why we define like a orthonormal basis.
It is.
So
This is the crazy sentence.
like that's basically it. That's like
Orthonormal basis of V. Yeah, exactly.
like there is like nothing more than it.
That's true.
Said three
So actually,
times in one
let's have them solve a simple example. So write this up. Let E1 to En be an orthonormal basis, and so just write E1 dot 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 En, and instead of orthonormal basis, write O dot N dot B, because orthonormal basis is too long. Okay, sure. Well, that's orthonormal versus orthogonal. You could in principle have an unnormalized basis. Okay, good. That would be perfect. Now, let V equals A1 E1 plus dot 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 whatever. Yeah, there we go. That one. Good. Question. What is V inner product E1? So you should write that down. V inner product EI. Yeah, V inner product EI equals question mark. Equals question mark. What do I replace the question mark with? Yes.
AI.
Yes,
Yep.
AI, that's right. So this is a very important idea, that if I have an orthonormal basis of eigenvectors, then I can figure out what the coefficients are of V by just inner producting it with EI. But important to note that the reason why we can do this is because these are orthonormal, meaning that kind of, if I take V expanded, all the cross terms go to 0 because they're orthonormal. That's important, but okay.
Wait, is that just like the component, right? Just be the
Yeah, I was
length
gonna
in
say
that
that.
direction.
Pardon?
It's just the length in that direction, right? Like.
Yes, kind of.
It's like, yeah.
But yeah, once again, remember, like how you check this is you plug in V, you use linearity in the first entry, and just every term with EI, EJ is 0 by EI being an orthonormal basis, right? So
So we can write like a vector
Yes.
like that.
this is important that we can write this for an orthonormal basis only. Yeah, that's right. That's right.
This is Pythagoras again.
And last one.
And you should, after you write the last one, you should take a sip of tea and let people absorb what has been written.
Just to make sure I don't mess up the yeah.
Is that a lowercase v or uppercase v?
Lower.
On the
Lowercase,
first line.
right?
Yeah.
Okay, I thought the vector space was something.
No. See, it's not a typo because it's obvious that it's not.
Okay, it was a little hard to understand what's going on.
That's maybe. You know,
Because I also didn't know if that
who,
was
who am I
V1
to
or
judge
comma.
what is difficult in linear algebra and what isn't?
Yeah.
Fedora still looks kind of.
That's okay. The more you write on a board, the better you will become at writing on the board.
Yep. So, any ideas how to like start proving that? Because like pretty straightforward.
I mean, let's not prove like, maybe prove one of them and none of the rest.
Well, like if you
Okay,
figure
the first one are they like
if-
just literally follows
the second follows from the first one.
I mean, it's all the same thing.
They're like, there's like a three-way if and only if.
I mean, it's not even an if and only if.
Yeah.
It's just, this is how it is.
It's a rewording of the
It's-
same
it's-
definition.
I mean, they're not equivalent statements. It's just if you have an inner product, it does, and this is an orthonormal basis, then all of these are true. So for an orthonormal basis, this is the case.
Yeah.
So I will start proving that.
So we have the thing, and then we just rewrite it like that, right? And then we use
But actually, I have no idea what the last one is. Is that the
This?
conjugate?
Yeah.
What was the last
yeah,
one?
it's just like this, but with n, like index n.
Whoa. It shouldn't be U, it should be V. One of them, because it's U with V, right?
Okay, yeah.
So
that is a-
something is, you wrote something wrong.
That is a typo.
That is a genuine typo. That actually changes.
Yeah, I think
Oh, yeah,
it's
that would-
V,
that should be-
comma,
Yeah, it should be V. No.
No.
That one's U, the other one's V. And in general, my advice is to, I mean, this is how I write V's. But if you write U like this and V like this, that's hard to tell apart.
Make
So
it
I
look
always write V's
Yeah.
like this to add the little
This.
things so
Or
that
what
we
about
can
this?
Okay.
tell apart.
Make a calm 60-degree angle.
Okay, no, but that looks ugly.
That's what the V looks like in like most places.
I don't know. I don't like it.
And then we
Just
and
like by the probably proved, this would be this.
Yeah.
and this by the one and that can be right.
Okay.
I don't have enough rant to memorize all of this. Scroll up.
These rules should. What do you mean? Which
Like,
rules?
These rules, like whatever these are.
No, the definition. You should have the definition memorized. It's very straightforward. You're linear in the first entry.
Uh-huh.
You're skew linear in the second entry, and
Okay.
and then the rest is as you would expect. Like v with v is non-zero or whatever. One thing actually that's kind of important. So in math, we defined the inner product here. The inner product was linear in the first entry, skew linear in the second entry. That's what math people do. In physics, they define it the opposite way. They define it to be linear in the second entry and skew linear in the first entry.
It doesn't really matter, does it?
Well, it doesn't really matter, but when you write things, you want to be consistent.
Ah.
And so
okay.
essentially what you have to learn is to be able to very easily switch and tell from context which is which. And hopefully by the end of it, you are able to kind of just write down, like just not worry about such things, like conventions, and just understand the convention from context.
Is there a reason behind this combination?
Hmm?
Is there a reason behind this combination?
The reason is I don't know. Physicists do one way, mathematicians do the other way. Probably
What's the last
because
step?
someone early enough,
I didn't go.
like probably someone writing papers in like the 30s, in physics used the other convention. Just like one of the early papers, they started using the other convention and it just cut off. That's usually how it goes. Yes.
Do I need to prove Gram-Schmidt procedure or just explain it?
Gram-Schmidt, you need to explain and maybe something so it's satisfactory. Something so that people understand, you know? Like, sorry, you know what? Actually, I'm being unclear with what I want. What I want is that maybe we don't prove everything, but such that after the end of this reading group, you understand the intuition and the definitions well enough, such that it is very easy for you to take the intuition and formalize it, right? A proof and an intuitive statement should not be too far away from each other. If you understand the thing well enough.
So
that's
the
goal.
textbook gives like some weird formulas, inductive formulas, but like Gram-Schmidt procedure is just like, as I said, so if we just take a random basis, it can be like any vectors, like in any directions, and that would be like some chaos. So that's why we want to like kind of make like a structure of orthogonal basis or orthonormal basis. And as I proved like at the beginning, the formula to rewrite like one vector u in terms of v and some orthonormal basis w. Gram-Schmidt procedure is basically it, but like for the whole basis of a vector space. So basically, it's like a way to rewrite one basis Vn to find like a formula and like prove that we can go from here to some beta tilde with orthonormal basis.
It's a change of basics matrix.
No, kind of.
No.
The idea is, we should maybe, before you explain the Gram-Schmidt, you should maybe give the statement of the theorem, right? Before you talk about it.
Yeah, it's a
And
long
the
one.
statement,
I will read it.
while you write out the statement, I will say what the statement is. So, we talked about these very nice orthonormal bases,
Yep.
right? But how do we know that these even exist in general for a vector space, right? How do you know that there exists a thing where everything's orthogonal and normalized and very nice? So the claim is that in a finite dimensional vector space, if you have a basis, then there's some procedure using which you can obtain an orthonormal basis out of that one.
Proof by construction.
Yes, it's approved by construction.
Okay.
So it's a way to, out of any basis, construct an orthonormal one. Okay? And actually, there's one important property that I will point out at the end that I think you will need to use, but, okay. Yeah.
If you want, right?
So wait, the procedure is just that you can always make a orthogonal basis, orthonormal basis?
If you have a basis, you can turn it into an orthonormal one.
Question.
But, and they're related in a particular way. Yeah.
A orthonormal basis. Is it like a corresponding one-to-one thing? So like for every basis there exists an orthonormal basis.
No, not necessarily, no. Well, it's not a one-to-one thing because I can take my basis, scale it,
Mhm.
and then I'll still have the same
Ah, okay.
associated orthonormal basis because it's normalized at the end.
You can also just work them backwards, right?
I'm answering too many things for you. You know, you're just writing things. You should be answering things too.
My bad.
I think what you meant to say is instead of up to Fn, it should be up to Fk minus 1, right?
Wait.
Yeah, that's okay. No rush. Fk minus 1 at the end. And this is important because we at the top Fn with
Mhm.
Fk minus 1. This is important because there's a particular property of this basis
Yep.
about the scans.
So, such that.
Spanning of
Yes.
E1. Equal to the span of E1 equal to
Don't just write n. N is usually the dimension of the vector space, so write k. No. Over there, because this holds for any k.
Wait, is that k equals from 2 to n?
Yeah.
Yes.
And then
all
just
all vectors.
F.
Wait, what about 1?
So we have f1. So you set f1 equals v1.
Okay.
And then I have an iterative procedure
Oh, I see.
of how to
Oh.
obtain
Okay.
fk from from f1 up to fk minus 1. And so give them a moment to write it down and then explain what this is doing and draw diagrams.
You just apply the thing from before every single time until you only have the last one left, right? And then that'll be your next one. So
Kind of. Fedor will
That's kind
explain.
of cheap.
Try. Okay.
You're right, Ivan. Maybe my tuition is bus.
There's something in linear algebra that looks hard in 240 or 247. It usually is. Except for when it is.
Try.
Maybe you want them to all start in the same point, or
Okay.
I don't know. Maybe.
So the first vector.
wait, why does that end up with a k?
What?
Why, the span one,
Yeah.
that's, why is that not iron?
Because-
it's true for any K.
Yes. So this is what's important.
Oh, like, and then you can do it all the way to.
So this is what's important of why if you have a given basis, V1 up to Vn, then when you write down this new basis, like the spans of the first two vectors is the same as the span of the new two vectors.
Okay.
Span of the three vectors is the same as the span of the three vectors. And this will have a very important consequence, which we will state in a second.
So as I said, it's basically the okay, let's do for just the lectures first.
So first, we just wanna project our vector of a basis V1, for example, to the so express that in terms of F1 and like some vector, so it's like
This is
orthonormal.
not quite right. Hold on. F1 should be what?
Oh,
V1.
V1. Okay.
Okay, erase that because that's not just
Mhm.
wrong.
Okay.
Okay, so write down what V1 and V2 are, like draw them. Like, yeah, just redraw it. Okay, good. So we start off by setting V1, E1 to be what?
To F1.
That's why it's not a change of base. Oh.
It's F1, but it's shorter.
Yeah, okay, so it's normal, like.
Yeah,
you
yeah.
only get one,
You
right?
good.
You build everything around.
Now what you
Mm.
do is you say, okay, let's take the second vector. I want to figure out what the second vector. Actually, you say it.
Yeah, I wanna figure out what would be the other vector that perpendicular orthogonal to the E1
Yes.
in that case.
And I want to use what to do it.
I want to use the like the projection T.
So, I want to use V2, right?
Yeah.
Because that's what I am given, to find a vector that will be perpendicular to E1. Do you agree?
No.
So, based on the previous logic of the previous thing that we did, what do we want to do now? We want to extract out of V2
Yeah.
V. You say it.
We want to extract out of the V2 the like F1 F2
Yes.
such that it's orthogonal to the E1.
Yes. So we want to extract. So, simpler words. You want to extract out of V2 the part that will be perpendicular to E1.
Yeah.
Okay. But how do I do that? I do that by subtracting the part in V2 that is.
That is.
Nothing. I don't know how to say it.
Yeah.
Yeah.
The thing that is like parallel to
Yeah.
V1.
That's basically a formula we like proved in.
Yeah,
the
exactly.
It's just
Yeah.
this over and
Yes.
over again.
Yeah.
But now when I have three vectors, when I get to the
Subtract
third
all the
vector,
parallel.
Yeah.
I subtract the part that's parallel to E1 and
And
subtract the
E2.
part that's parallel to
And you're left
E2
with
and look
this.
at what's left.
Mhm.
And you just keep doing this until you're done.
Yeah, that makes sense.
Okay.
My intuition is so broken. Why it's like hella simple.
Yeah. Have you seen Graham Schmidt yet in 247?
Nope.
No.
Okay,
Haven't
well,
seen
now
it
you know
in
what-
our cases.
You now know things that you'll do.
So
Schmidt,
yeah.
not Smith.
And the last one is the Cauchy, Schwarz, Bunikowski inequality.
Okay, wait, sorry. I didn't finish. There's one
We're doing
comment.
CS.
There's one comment. You mean we're doing linear algebra? It's not CS.
No. I come from math. Like competitive
Yes.
math, Cauchy Schwarz, there's some generalization for inequalities.
Yes,
But I
and
thought
then
there's
it's
a
just
for
yes.
vectors.
Sorry. There's one comment that you didn't read about, and I forgot, but
Okay.
it is a very important comment, so I will make it now. So, how does this thing work? Let's look very carefully. So I see This is yeah, sure. I'll write it here in yellow. So I want to just expand a little bit on this. Do you agree? So I see I have that F1. I had a basis V1 up to Vn. Do you agree?
Yeah.
And then I obtained E1 up to En, where this is now orthonormal. Do you agree?
Yeah.
Okay, good. So, and how did I do this? You know, E1, it was in the span of V1.
Yeah.
Do you agree? E2 was obtained from V2 and E1.
Yeah.
Do you agree? But E1 was obtained from V1, so E2 was obtained from V2 and V1.
So it's in the span.
So E2 is in the span of these two. E3 is in the span of these three, and so on and so forth. And so I get this property, that the span of these is the same as the span of these. Okay?
Yeah.
And so this is kind of the key relation of this basis and this basis. You should know this because you don't know this column.
Okay.
Okay. Now, suppose I had some linear operator t, some t on V, and I wrote the, and then t was upper triangular with respect to some basis. Do you agree? So V was upper triangular with respect to some basis V. People remember what this means. This means that T Vj is in the span of what? V1 through Vj. Correct. That Tvj is in the span of V1 through Vj. What does this mean? This means that if I write the matrix for Tvj in the V basis, right? This means that, so this is the jth kind of entry. I have non-zero stuff up to the jth entry, and after that it has to be 0. Right? Because it's in the span of Vj, I don't need any vectors past that to explain what Tvj is. Okay? So now the claim is, if this is the case, implies there exists an orthonormal basis, E1 up to Ej, such that T is upper triangular with respect to this basis as well. This new basis E1 up to En. Okay? So if T Vj is upper triangular with respect to some basis, then it has to be upper triangular with respect to an orthonormal basis. And this orthonormal basis you obtain from this one with Gram-Schmidt. Why is this clear? Because look, if T Vj is in the span of V1 up to Vj, right? Then if I wrote T Ei, right?
Yeah.
T Ei is in the span of, so I'll write the proof. So T Ej, right? Ej is in the span of V1 up to Vj. Do you agree?
Yeah.
But TV1 up to TVJ is in the span of V1 up to Vj. Do you agree? So this means Tej, okay, it's equal to some, whatever, linear combination of the VI's, right? Because, with coefficients given by whatever, but some linear combination of VI's, I equals 1 up to j. Do you agree? But then each of these is in the span of V1 up to Vj. So actually, maybe I should use like this. Whoops, this should be in here. Okay? But this means that this has to be all in the span of V1 up to Vj. Okay? But we showed that this span is equal to this span. So this is in the span of E1 up to Ej. Do you agree?
Yeah.
So this means that in this new basis, the matrix is still upper triangular. Okay? Makes sense. Why is this so important? Recall what we talked about on day 1. what did we show about upper triangular matrices on day 1? You weren't there, that's okay. For a vector space over the complex numbers, any operator has a basis. Yes.
Quadrangular?
Yes. So the fact that we proved in day 1 proved we already know if V is over C, okay, is over C, and V is finite dimensional. This implies that what? That T, any operator over V is upper triangular, is upper triangular in the sense that there exists a basis with respect to which its matrix is upper triangular. So this is something that we proved on day 1. If T is finite dimensional over C, there has to be a basis for any matrix in, such that it's upper triangular. This was a consequence of the fact that you can factor any polynomial with complex coefficients. It came out to be a consequence of that. Maybe you should read the appropriate chapter in Axler or thing. Okay, or watch the video. We have a video. But now, combine this result with this result. We now have that for any operator T over a complex finite dimensional vector space, there exists an orthonormal basis with respect to which T is upper triangular. And using this fact, we will prove the spectral theorem next week in like 2 lines, which will be very useful. So you should, this is a very important result that is kind of, and whenever you use spectral theorem, you kind of use this in some sense. Okay, but no one ever thinks about this when they use spectral theorem, so it doesn't matter. But yeah. Okay.
So
Hold on, give them a moment,
yeah.
because there's, you shouldn't look at me, you should look at them. And you see that they're still writing, then you should probably, that's why you have T. You should, unless you don't like the T, in which case you should tell me so that I get a different T. But I actually kind of like this one.
What does that say?
Wait, so let's see.
go.
What's your question?
Cauchy sorts.
Yes.
Oh.
AU, wait.
AUC.
Okay.
It's CHY.
CHY.
Yes, because in French, CH is sh sound.
Okay.
That's just see on Wikipedia. Oh my god.
Schwartz.
It makes sense.
I think it's with a Z at the end of stuff.
Schwartz.
Schwartz is with a Z. Yeah, I agree.
And
Transliteration doesn't make sense. Mhm.
Yeah, so it says that for any 2 vectors, this inequality is true, and it becomes an inequality when one of the vectors is a scalar multiple of another.
Okay, just small things so we're all on the same page. U inner product V is what kind of number?
Real.
A scalar.
Is it a real number?
Just a scalar?
Did we say F over reals? It's in
It's-
math, right?
It could be complex, right?
Yeah.
Which is why you have the absolute value around it. That's an absolute value of a complex number. And by absolute value of a complex number, I literally mean like it's a plus bi, so I
Yeah.
mean a squared plus b
Yeah.
squared square root of that.
Yeah.
Okay. And on the other side, it's the norms. So u inner product u square root. Okay.
So,
Proof.
We can express U as basically the Gram-Schmidt procedure.
plus some, like, this whole thing plus some W. And then using the Pythagoras,
We got this.
And this thing, and this thing. Mhm. So, do you see that, or not really? I can rewrite it.
You know what is a better way to do this maybe? How I would try and do it? It's more pedantic, but start with U inner product V, and then kind of.
But I'm almost done. Like, okay.
Yeah, no, that's fine. That's
Yeah.
fine. Sorry, I shouldn't interrupt you.
So, and then since we know that this this is at least 0, we can just say that this whole thing is this, right? You don't see that, right?
And we have once forgotten about these people.
Oh, did you, Fedor,
Mm.
did the norm move to just the top at the end? Or like,
Here?
yeah, the last time. Like,
Here.
with the V squared though.
So we just say that. Wait, give me a sec.
Okay.
So we just say that this is at least 0. That means this whole thing is greater than or equal to
Yeah.
just one term.
Mhm.
This goes here, so it goes on the same.
Yeah.
And then we have this vector, and then this. Which is basically what we want. Like, see,
Yeah.
that's it.
So why is this like small comment about why this inequality is very powerful? Is the small comment particularly hinges on the fact that you forgot to give an important example of an inner product space earlier. One important example of an inner product space. Yeah, I'll just say it. It's fine. So we'll just go a little faster. One important example of an inner product space, which it actually would require quite a bit of effort to prove that this is indeed an inner product, and it's actually not, but it is as far as we're concerned, is if you have this L2 space, big L2 on, say, I don't know, the real line. Well, actually, no. Whatever. It's all functions from the real line into the complex numbers, such that f like this, f of x dx was this integral was finite over the whole real line. Okay, so it's kind of you take f and then you just take the norm squared in terms of the complex numbers. Okay, so it turns out this L2 space is indeed an inner product space, where the inner product is given by. Okay, see, I'm already using the physics notation, but that's fine. Where this is the inner product. And this is a space that we will see appear in physics time and time again, all the time. And okay, technically it would already be very annoying to prove that this being finite implies that this is finite. That would be, I mean, that would really be kind of equivalent to proving the Cauchy-Schwarz inequality for this. So, whatever. But suppose you knew that this was finite and well-defined and everything was nice. In fact, actually, maybe if you didn't want to prove that this was finite, you would, instead of R, like do this on like an interval, let's say, from 0 to 1. like look at all bounded functions on the interval from 0 to 1 that go into C, and then you will automatically have all of these integrability conditions, and that will be fine. And so then, what you would immediately have then, okay, you can define this as an inner product. You can show it has all the linearity properties. You can show that this is well defined because it's finite, because the functions are bounded, so this integral doesn't diverge. Okay, very nice. And then what you would immediately have from Cauchy-Schwarz, you would have this. You can do, okay, right? So this is equal to what? This is equal to the absolute value of this integral. Do you agree? Should be less than or equal to the square root of this integral times the square root of this integral. Okay. And these kinds of inequalities end up being like very useful and appear fairly frequently. And kind of see if you were if someone gave this to you in an analysis course and told you, hey, prove this inequality, you would spend all of this time thinking about like some partitions and like trying to bound something and taking refinements. I mean, you haven't seen this in 157
No,
yet.
that's just that, right?
Exactly.
My form,
but exactly.
my form is just
Exactly. But if you so if you try to prove this using analysis, it would be very annoying and complicated. But if you just say, if I manage to show that this is an inner product and it's fine, then you just get this immediately from Cauchy-Schwarz. So the point is, this inequality looks simple. In fact, crazy non-trivial when you apply it to slightly non-standard vector spaces. When by slightly non-standard I mean anything that's not Rn or Cn. Okay. So this inequality is in fact non-trivial, and it's in fact like every inequality is actually that inequality, except for like some minor exceptions.
And the last one is triangle inequality.
Yes.
wait, what?
So far what we have done is we defined the norm as the square root of V inner product V, right?
So
But
just
go ahead.
So since in the beginning we introduced like a norm in a way that we didn't involve inner product, as a as an axiom, like a property of that norm was triangle inequality.
Yeah.
So now we want to be sure that the triangle inequality holds in
How we define
in inner product.
and how we define the norm from the inner product.
so
So that's not.
so this is just this. It's just like a norm squared. And what is this? And this is already looks like a quadratic formula, basically. So we have u norm squared, u norm squared, and we have this. But we can rewrite one of the terms as a conjugate of another, basically. And the thing is that the like real part of them will be the same as a conjugate. That's why this whole thing can be rewritten as a which is basically the quadratic formula.
Oh wait, a little bit.
So that would be greater or equal than, yeah, we can say.
Yeah, let's go ahead. Whoa.
Yeah.
Whoa.
Yeah, my name is.
Oh yeah, okay.
Oh, because they.
It's not just two, there's more, right? You're about to write more things.
Yeah.
Okay.
Yeah.
Sorry.
And then this, by the Cauchy-Schwarz-Minkowski, would
Yeah.
be plus. And this is the color from. So we got that.
You just take square root of it, and you'll get the triangle body.
That's good. So, can you do a quick summary in the same way that I said about like, remember I drew a diagram of like inner products, norms, metrics, and make the comment that I made last time.
Okay, I'll try.
So we got roots. Then we can define norms. And for them, metrics.
So, if I look at this diagram, what's a natural question I want to ask? What's a natural question to ask about this? I can go from inner product to norm and then to metric.
Can you go backwards?
Exactly. That's a very natural question to ask.
Is it
Can I go
invertible?
backwards? So the question is, can I go backwards? If I have a metric, can I construct the norm? That's the first question to the audience.
Did you discuss that? I don't remember.
I did make a comment about it. So
You can
if
go
I have a
from-
metric, yes.
Can you just go from 0 to 0 backward? Like, probably the distance from 0 backward? to
Yes.
0 norm?
However, what are metrics defined on in general?
2 points.
Metrics are just defined on a set.
Set of
Oh, yeah.
Set
Yes.
of numbers.
So first of all, that doesn't even always make sense unless your space is a vector space, right?
Yeah.
This question doesn't make sense unless you're on a vector space. And then if you are on a vector space, then does a metric necessarily give you a norm? So a metric works nicely with what? With addition. So that's okay. But what's the other one you have?
Multiplication.
Multiplication. Do metrics know about multiplication?
No.
No, not necessarily, right? I could have some metric, which like on R2, you could imagine a metric where for some reason kind of points that are really far away are considered to be really close, and points that are really close are considered to be really far away. Or, actually no, sorry, that doesn't work. That's a lie, that's not possible. But somehow like points aren't uniformly close or far away. So like I do like, I don't know, like it doesn't fall off like square, it doesn't go like square root of the distance. It would go like, sorry, it doesn't go like r, but it would go like some function of r, the distance to other points. So not necessarily, metrics don't necessarily induce norms. Next question, do norms give you inner products? Probably not. Intuitively, why? Norms tell me something about
The length.
the length. Inner
But inner
products.
product has information on like a direction distance, like into you,
It,
like
yeah,
order.
it tells you the angle between two
Yeah.
vectors, right? Norms just tell you about lengths of
So
vectors.
it doesn't have a direction.
Yes, so norms, not all, you can have norms that don't come from inner products.
Yeah.
If you read Axler, he does talk about like what condition has to be satisfied for it to be whatever. But okay, you can read that, you cannot read that. Up to you.
That's it.
Yeah. It's okay.